Assalamualaikum and hi. My name is Nur Aisyah binti Zulkifli. My project entitled Microstructure and Corrosion Behavior of Aluminium, Zinc, Magnesium and Stannum Casting Alloy for Sacrificial Anode Application. Here is the outline of my presentation starting from introduction until conclusion. Firstly, for introductions. Sacrificial anode is a method of preventing and protecting metal from corrosion. It is widely used in hull of ship, offshore pipelines and production platforms. The anode corrodes by sacrificing itself in order to protect the cathode. Pure aluminium widely used as anode, but the formations of oxide layer reduce the efficiency of the anode. The figure shows the sacrificial anode before and after the corrosion. Next, for problem statement. Pure aluminium decreases its efficiency in sacrificial anode application due to the formations of oxide layer on its surface. Thus, the additions of other elements such as zinc, magnesium and stannum promote the breakdown of oxide layer and increase its efficiency. Sacrificial anode application is a method that uses two different metal alloy which are anode and cathode alloy. The anode metal will sacrifice itself in order to protect the metal from corrosion. The figures show the sacrificial anode in hull of ship. Different types of alloying aluminium will have different corrosion behavior. The presence of intermetallic compound in the alloy gives different mechanical properties and corrosion behavior as anode metal. The characterizations of four-type alloy with the formations of intermetallic compound during solidification process were investigated in order to obtain the best alloy to be used as anode in sacrificial anode. The objective of the project are: firstly, to examine the hardness and corrosion behavior of four different aluminium alloys. Secondly, to investigate the effects of alloying element on microstructure development due to the formations of intermetallic compound on its growth of four aluminium alloys. Thirdly, to determine the best aluminium alloy used for sacrificial anode application. Next, for methodology. The figure shows the flow charts of raw ingots of four types of elements undergo casting process and several tests and analysis. Consists of Vickers hardness test, corrosion protection test and microstructures analysis. The table shows compositions of aluminium alloy. In this project, there were four types of sample alloy. For sample preparation, which is casting process, the video shows the casting process for sample 4 had been done.
Aluminium were inserted into crucible furnace at 720 Celsius, followed by zinc ingots, stannum ingots, and lastly, magnesium ingots. The multimeter was stirred manually to get homogeneous mixture. The multimeter were poured into the preheated mold and allowed to be cooled at room temperature.
The sample shows after the casting process. After the casting process, the sample undergo cutting process, then continue with grinding process using different grade silicon carbide paper. After grinding, the sample was polished using monocrystalline diamond suspension. So the figure shows the sample after grinding and polishing process that has mirror-like surface. The first test is corrosion potential test. Multimeter was used to measure corrosion potential value against a column as reference electrode in natural seawater. Decreasing in corrosion potential value increase the electronegativity of an alloy, thus increase its tendency for alloy to corrode. Next, the Vickers hardness test. Different offloading value were applied to all four samples to investigate their hardness. Increasing in hardness value of the alloy is due to the presence of intermetallic compound. So, the video shows the Vickers hardness test has been done.
The figure shows the part in micro Vickers hardness machine consists of objective lens, diamond indenter, and micrometer. The samples was indented with desired indentation load. The objective lens shows the shape of indentation. The screen reveals the hardness value, load of indentation, and value length of indentation shape.
The optical microscope analysis. It is used to analyze the microstructure of alloy using different magnifications. The presence of intermetallic compound in the alloy enhances the sacrificial anode application. Lastly, for scanning electron microscope analysis. It is used to analyze the microstructure of alloy due to the formations of intermetallic compound. Next, we move to result and discussion. Firstly, for corrosion potential test. The graph shows sample 1 shows the highest corrosion potential value, which is negative 0.818, followed by sample 2 and sample 3. whereas sample 4 had the lowest corrosion potential value, which is negative 1.267. So the additions of stannum produce an alloy with the most electronegative value. The higher the electronegativity value, the higher the tendency for the oxidation process, which is corrosion, to occur on the alloy surface. Thus, sample 4, which is aluminium, zinc, magnesium and stannum alloy, is the best sample for the use of sacrificial anode, where it will be sacrificed in order to protect the cathode. For viscous hardness test, the graph shows the highest hardness value was sample 3, but the additions of stannum to form sample 4 causing slowly decrease in the hardness value. The increase in the hardness value for sample 3 is due to the formations of magnesium zinc base type intermetallic compound that act as a strengthening phase. Additions of stannum causing slightly reduce the hardness value in the sample 4 because stannum promote the active corrosion behavior of the alloy in protecting the cathode structure in seawater. Additions of zinc, magnesium and stannum affect the intermetallic compound of the alloy and influence the mechanical properties and corrosion behavior of the alloy. Thus, sample 4, which is aluminium, zinc, magnesium and stannum alloy, is the best alloy for the use in sacrificial anode application. In optical microscope analysis, the figure shows the micrograph of 4 alloy. It shows that additions of elements such as zinc, magnesium and stannum cause refinements of grain size. Sample 1, which is aluminium pure, had the biggest grain size, whereas sample 4 had the smallest grain size. Formations of intermetallic compound in sample 3 and sample 4 known as Mg2Sn, which increase the hardness value and promote the corrosion behavior to occur. The figure shows the presence of intermetallic compound in sample 4 at different magnifications. Intermetallic compound, which is Mg2Sn, enhance the sacrificial anode performance of the sample 4 by promote the breakdown of passive oxide layer, thus increase the corrosion behavior of the alloy. Sample 4 is the most suitable alloy as anode in sacrificial anode application because the refinements of the grain and formations of intermetallic compound increase the hardness and promote the efficiency of sample 4 to corrode. For SAM analysis, the figure shows the micrograph of 4 types of alloy. Additions of alloying elements such as zinc, magnesium and stannum in pure aluminium influence the formations of intermetallic compound and grain size. Sample 4 had the highest number of intermetallic compound and the smallest grain size compared to other samples. Sample 3 shows the formations of intermetallic compound, which is Mg2Sn. So the additions of stannum to form sample 4 cause formations of stable Mg2Sn phase. Figure shows the presence of stable intermetallic compound known as Mg2Sn in sample 4. It was proved by the EDS analysis. The bright spot known as Mg2Sn phase located especially at the grain boundary. Additions of stannum in sample 4 react with magnesium but rejected the interdendritic structure to form stable Mg2Sn. The decrease in the hardness value slightly, but increase in the electronegativity of sample 4 to corrode. So sample 4, which is aluminium, zinc, magnesium and stannum alloy, is the best alloy used in sacrificial anode application because the formations of stable intermetallic compound increase the efficiency to corrode. For application in industry and society, sacrificial anode application widely used in various industries such as hull of ship to prevent them from corrosion. The video shows the sacrificial anode application in hull of ship.
To prevent the ship from corrosion, the sacrificial anode is placed at the bottom of ship which is exposed to seawater. The anode will corrode first instead of the steel of ship.
The figure shows the anode before corrosion and after the corrosion. Aluminium, zinc, magnesium and stannum alloy is the best anode in sacrificial anode application as it is very economically by preventing the ship or structure from corrosion and reduce the cost of maintenance by prolonging the lifetime of the ship. The conclusions of the project are: additions of alloying element in aluminium alloy affect the formations of intermetallic compound which influence the hardness result, corrosion behavior and microstructural development for different aluminium alloy. The presence of stannum in aluminium, zinc, magnesium and stannum alloy rejected the interdendritic structure, thus forming a stable intermetallic compound alloy and promote the active corrosion behavior, thus increase the hardness of alloy which are suitable for sacrificial anode application. The formations of intermetallic compound in the alloy increase the efficiency of the sample 4 as a sacrificial anode by break down the outside layer. Sample 4, which is aluminium, zinc, magnesium and titanium alloy, is the best candidate for the use as sacrificial anode because it has highest electronegative corrosion potential, good hardness test and formations of intermetallic compound which is easier to corrode, especially in the seawater compared to other alloys. This is the list of references that I refer during my project work. I think that's all from me. Thank you.